Okay, I mentioned last time we're going to start on this video talking about parallel axis theorem. And so we mentioned last time that there is, in your text, you will find that for most standard common shapes, the calculus, so to speak, is often done in that. So if I've got a triangle here where this is 1/3 my height and 1/3 of my base, where the centroid of this triangle might be, that if I take the axes, let's say the x prime axes and the y prime axes, passing through that centroid, these are the axes passing through that centroid, that what I can do is I can convert the moment of inertia about the x prime axis, or the moment of inertia about the y prime axis, to any x or y axis, ix and iy. What I'm saying is, inside your cover of your textbook, you've got these moments of inertia about all these different shapes, where they provide the moment of inertia about the axes passing through the centroid of this object. Now, remember, we've just solved a problem. We said, well, if my x-axis is down here, I've got this triangle here, goes up h and b over here, height h, base b. And if I want to know the moment of inertia about this x-axis, what I can do is I can take the moment of inertia about the x prime axis, which passes through the center, and it's going to be 1/3 h is going to be the distance between those two axes. If I take the moment of inertia about this x-axis passing through the centroid and add to it the area of the shape, multiplied by a quantity I'm going to call d sub y. It's not dy, it's not a differential in the y direction. It's technically kind of the distance in the y direction. I like to call it d sub y because I don't want to call it dy. I don't really feel like it's the same thing. It kind of is, but it's not really the same thing. In this case, this dy is this 1/3 h. And we can prove that, right? So if I say that I want to know this ix, and if I look inside the textbook, well, let's do this. Let's if I know for any triangle, ix prime we've found to be, or you can find in your textbook to be bh cubed over 36. That would be the moment of inertia about this x-axis. Now, I've already found the moment of inertia about this axis, but let's put this to the test because I already know this, and I found this inside the cover of my book. So let's let's compute it using this method and see if we get the same answer. If we do everything right, we should. Be a nice check. So let's find this moment of inertia about this x-axis, because I know it about this axis from the textbook. That is bh cubed over 36. That is ix prime. Let's add to it the area of this shape. The area of the shape is 1/2 base times height. That's the area of the triangle. And I want to multiply it by the distance between the two axes. That's what this d sub y represents, is the distance between these two axes. These are both x-axes, so this would be the distance in the y direction squared, and this distance then is 1/3 of h, and that's going to get squared. Okay, so let's do some math. Let's math the math here. bh cubed over 36, we're not going to touch that guy yet. Let's simplify this quantity here. So this is going to be, I'm just going to leave 1/2 BH alone for the moment. And we'll go ahead and cube or square this guy. We'll square this guy. This is 1 squared is 1, 3 squared is 9, and I'm squaring the h. So I'm just going to write it this way. I'm going to square the h. You can square the 1 also. So it's h squared times 1 squared. And the denominator here, again, I'm squaring this guy. So the denominator is 3 squared. So it's going to be h squared over 9. Okay. BH cubed over 36 plus 1/2 BH times h squared over 9. And so we're going to simplify this out. Ix is going to be BH cubed over 36 plus is going to be 1/2 of 1/9 is 1 over 18. And on top I'm going to have BH cubed. Oops, sorry. So this is going to become then the 2 times 18 is 36, so my common denominator is going to be 36. So this is BH cubed over 36 plus 2BH cubed over 36. 2 times 18 is 36. This is going to equal 3 over 36 BH cubed, which is going to become BH cubed over 12, which is what we found earlier through using calculus methods. Calculus, heck of a thing, it works. How about that? All right, so that's very rapidly fundamentals of parallel axis theorem. I know the moment of inertia because I can go look it up. The moment of inertia for any triangle through its centroidal x-axis is going to be BH cubed over 36. Now, this also works in the y direction. And this also works in the y direction. The idea of the parallel axis theorem is that I can find the moment of inertia about any x or any y axis for any shape if I know its moment of inertia about its centroidal x or y prime axes, or both. I add to it the area. In the case of the x-axis, it's going to be a distance in the y direction, d sub y squared. And if I've got two y-axes, the distance between them, so it's going to be area times d sub x, the distance in the x direction between the two y-axes. So again, any random shape that I've got that I happen to know the moment of inertia for its x prime and y prime axes, the axes passing through its origin. The distance between the y-axis, which I want to know the moment of inertia about, and its centroidal axis is going to be d sub x. And the distance between the x-axis and the centroidal x-axis for the shape is going to be d sub y. So based on this information, I can go look up moment of inertia for a bunch of different shapes, add to it the area times the distance between the axes squared, and that gives me the moment of inertia for any axis. So the beautiful thing is I don't have to do all the calculus all the time. If the calculus is already done for me, I can just employ it for if a moment of inertia is known about the object's own centroid, then I can just employ this to find moment of inertia about some other axis. And that's going to come in very handy then when we talk about using composite bodies to find moments of inertia. I'm just going to put that on the next video because I got to pull out another stack of notes to get there.